Section 5.2 is exponential functions and graphing. It's the last section before exam number 3. So we just had done our 5.2a, 5.2b kind of thing about exponents and what they mean and so forth. So let's read what's going on here. It says, the function f of x equals a to the x, where a is a real number, it's greater than 0. It's not 1, because if it was 1, that would be really boring. It's called an exponential function. So the base is called a, right? And the x is the exponent. The base needs to be positive, so that's important, in order to avoid complex numbers. And you're like, well, why in the future, okay? So this has to do when we go for inverse later. So for inverses later. So whenever we have an exponential function, guys, the base will always be a positive number, all right? So here's some examples. The following examples are of exponential functions. So we have a base of 2, notice it's a positive number. We have a base of 1/2, it's a positive number, and a base of 3.57. So just notice it doesn't have to be a whole number. It can be a fraction or a decimal, but all of them are positive. All right, so what I want to do is we're going to do a table, but with both of these, when we do a table, you're going to see a pattern going on, all right? We will graph 5 points in our table initially, but when you go to graph these, you really only need to graph 3 points, all right? So we'll do x, y chart. We'll pick -2, -1, 0, 1, 2. And what's cool is that we just got done doing negative exponents, so we know what this does. So what is our function? It's 2 to whatever power the x is, okay? So this is 2 to the -2 power. But if you remember from yesterday, negative power just means you go on the bottom, right? So this is actually 1/2 squared. But what is 2 squared? 4, so this is just 1/4. So the point we would plot is -2, 1/4. And then the pattern continues, right? 2 to the -1 just means it needs to go to the bottom, so that's just 1/2. 2 to the 0, anything to the 0 power is just equal to 1. We learned that yesterday. 2 to the first power is just going to be 2. And 2 to the second power is just going to be 4. All right? So we'll plot these 4 or 5, and I'll tell you what ones you'll just worry about later on. So -2/4 is barely above the x-axis, so it'll just go right here, kind of sit on top of it. -1/2 is obviously halfway up our block. 0, 1 will be right there at our y-intercept. 1, 2 will be right behind them. And then 2, 4, so go up 4. You'll see a pretty quick growth there. And that's the whole idea of exponential functions. They start kind of shallow, almost like a horizontal line, where the x-axis is the asymptote, but then they shoot up pretty quickly.
Are we going to be able to use a calculator on this?
On the test? I think I'm going to have a non-calculator and a calculator part.
Would this be on the calculator part?
It's a good question. I'm not too sure yet. Can I answer that next week?
Sure.
Okay.
Because I don't know, like, if I want to have to do, like, I don't understand, like, a -1/2 and all that.
Oh, well, you were here yesterday, right?
Yeah.
So whenever we learned about negative, so you are okay with when we pick an x, that means it goes into the function wherever x is? Is that okay? And so in this case, since it's an exponential function, the variable is actually in the exponent. And we just learned yesterday that a negative screaming, I'm in the wrong spot, right? So that means instead of 2 being up on the top, he needs to go in the basement and be happy and become positive. Right? It's just everything we did yesterday. So a negative exponent just means you need to go to the bottom, or if you're in the bottom with a negative exponent, you need to go to the top. What I wanted to point out, let's do this next one, but then I'm going to point out a pattern, and you'll be good to go. Okay, so then we're going to do the same thing, x, y, and we're going to pick the same x's, -2, -1, 0, 1, 2, but something's going to switch, okay? So we're going to take 1/2 to the -2, but if you remember from yesterday, this means the whole thing's in the wrong spot. So how can we write 1/2 to the -2nd power with a positive exponent? What do we have to do to 1/2? Flip it. So this becomes 2/1 to the 2nd power, or just 4. And Braden, this is kind of like what you're talking about too. So if 1/2 the whole thing means the whole thing's the negative, it means the whole thing's in the wrong spot, so we just need to flip it. And that's what negative exponents essentially are, okay? And then this is just 2, 2 squared is 4. So if we're going to do the same thing with negative 1, 1/2 to the negative 1 power just becomes what?
Like 2 over 1?
Yep. Just to the first, right?
So it only affects the number in front of it, and that makes
Right, so,
the exponent.
so the exponent goes with whatever is directly to the left, right? So in this case, the whole number 1/2 is directly to the left, but it means the whole thing is in the wrong spot. So the 1 needs to go to the bottom, the 2 needs to go to the top, and that's what happens. We just end up flipping it. What about 1/2 to the 0 power?
That's just 1.
That's just 1. What about 1/2 to the first power? That will just be what? 1/2. What about 1/2 to the second power? That will be 1/4. Square both parts. So notice they end up being the exact same y values, but flip-flopped. So this is actually the same graph that we just graphed above, but it's reflected about the y-axis, okay? So negative 2, we're going to be at 4. 1, 2, 3, 4. Negative 1 will be at 2. 0, 1, 1, 1/2, and then 2, 1/4. And again, it's almost like this horizontal graph there, but when it starts to shoot up, it really shoots up. So the x-axis is a horizontal asymptote. We'll write that off to the side. They don't really stress that too much in this section.
Will we have imaginary numbers?
We will not graph imaginary numbers, ever. Okay? So that's good to know. Because that's where you're like, where does this come from? So one thing I wanted to note on both of these graphs, guys, is really if we can just graph these three in the middle, we'll get the general shape of the graph. What number is always in the middle? The point 0, 1, right? It doesn't matter what your base is. When you raise it to the 0 power, it'll be 1. So 0, 1 is always going to be on your graph. What else will always be in your graph? Your base to the first power, okay? So depending on what that base is, you might be up high at 2, you might be down low at 1/2. And then what else will always be on there is the reciprocal of your base, right? So when we graphed 2 with a negative 1, it's reciprocal, 1/2. And we graphed with 1/2 with a negative 1, it was 1/2 reciprocal, 2. Those 3 points will give you the shape in general. And the reason why I'm pointing that out is because here in a second we're going to start doing stuff with shifting, like left, right, up, down. If you can just move those 3 points, you'll get what your graph is doing. All right. Yep, that's fine. So here, what we have is just something that I want to note for the pattern is, okay, I didn't point it out, but we have it. You don't know how to flip it. Notice when we had a base of positive 2, our graph was low on the left and shot up on the right. But when we had our base of 1/2, it was high on the left and went down low on the right. And notice that's kind of what this all has in common. So if your base is a number between 0 and 1, so it has to be bigger than 0 because it can't be negative, but 0.4, 0.25, 0.7 are all less than 1. Notice all the graphs start high and then go low. Okay, so let's write this down. Our base A is always between 0 and 1. So A is the base, remember? And then over on the right side, what do you notice about all the bases? 4, 2.5, 1.8, they're all bigger than 1, right? So if your base is bigger than 1, you'll start low. And again, it's just to kind of keep notes so you know what the parent function is. So if the parent function starts with a base between 0 and 1, you know it goes this direction and vice versa. All right, so here's some rules, again, to kind of just keep in mind. Patterns that we've already seen taking place. If x is 0, anything to the 0 power gives you a y value of what? 1. We saw that on both graphs, right? 0, 1 was a point on the graph. The function value, the y, approaches what but never equals the y equals 0. So therefore, there's a horizontal asymptote at the x-axis. Because think about like when you're solving, like what could you put as an exponent to make your answer 0? There's nothing, right? You put negative exponent in, it makes it a fraction. If you put a positive exponent in, it makes a big number. If you put 0 in, it just makes it 1. There's no way to make an exponential function equal to 0. So that's why we just approach the x-axis, but we never cross it. All right, last one here. If the base of the function is less than 1, it takes the behavior of reflection over the y-axis. So we don't really get to see it here because none of them are complete opposites. But if this was like 1/2 base, it's the same thing as 2, like what we did on the front. These had the exact same y values. They were just reflected about the y-axis. All right. This is kind of random, but I thought it would be interesting. This just shows you a real-life exponential function. So real-life exponential function. So even though when they graphed it, so let's look at what the graph is. It's the number of cell phone subscribers at the end of the year. So notice down here in the 80s, before you guys were even born, it's very, very low. The number is in millions. But then somewhere right around here, the late 90s, early 2000s, it starts to shoot up. So even though they're graphing it as a histogram, meaning bar graph, it has the general shape of an exponential function. So they would say cell phone growth is growing exponentially, and that's a term that people use, meaning very quickly. Because linear is just pretty constant, right, at the same time every year, where this one's like, woo, shooting up. I would say the same thing for probably like internet usage, like apps and stuff would be kind of the same idea, where you would just see this point where it just shot up a lot. All right, so this is what I was talking about. What we're going to start doing is we're going to start graphing these, and it might be one of those things, Brayden, where I let you use a calculator on the test, but as long as you're showing me your work, okay? Because you could just flat out put this in your calculator, 2 to the x minus 2 power graph, and be like, ta-da, I did it, you know? But if you have something like this where you show me kind of the base, what the original one looks like, and the shifts, okay? So the parent function, I'm going to write it down here, is the one that we just graphed on the front page. So the parent function it's just y equals 2 to the x, right? We don't have any shifts. The base is 2, our exponent's x. So this is what I want you to remember when it comes to graphing, okay? Just the 3 points, -1, 0, and 1 for your x value. So we know if that exponent is 0, 2 to the 0 power is always what? 1. So we know he's always our middle point. And then if your base is bigger, when you raise it to the -1 power, it makes it a fraction, the reciprocal, right? So what's the reciprocal of 2 when you flip it? You get 1/2. So at -1, our y value was 1/2. And then it's easy to raise that same base to just an exponent of 1. What's 2 to the first power? 2. So see, by doing this, you can see which direction that's going. It's going to be down low here and go high, and that's enough to graph it. If you want to go more, you can. Typically, I don't go more in the negative because it gets really small, but it's not hard to say what's 2 squared. 2 squared is 4. That would be easy to graph. And you really get the shape of the graph, okay? So this is just the parent function, where he's growing exponentially off to the right and kind of plateauing off to the left. So this is just taking in our transformations that we learned in chapter 3. What is this x minus 2 doing up top? Is this on the inside or the outside of the function?
To be on the inside.
It is the inside, right? If it's on the outside, you just have a big -2 behind it, right? So since it's on the inside, is it a shift left and right or a shift up and down?
No, it wouldn't be left and right.
Left and right, and it's the opposite of what you think. So -2 is actually shifting at which direction?
Right.
To the right. So how are we going to graph this? We're going to just shift it right 2 units. So you know those 3 points that we just plotted? We're literally just going to shift them over 2. So this was at -1, 1/2. So I'm going to go 1, 2. Now it's at 1, 1/2. This was at 0, 1. So now I'm going to go over 2, 1, 2. So now it's at 2, 1. This was at 1, 2. But I'm going to go over 2. So now it's going to be at
3, 2.
You got it. And this was at 2, 4, so now it's going to be at 5, 4. So see, you have still the same general shape, but where you start increasing has been shifted to the right a little bit. Both of them have still a horizontal asymptote of y equals 0. We'll just make note of that. They don't really ask us, but I like to kind of pull that in because we're still talking about that. Okay? So see how, like, as long as we know the parent, we're going to be able to do all kinds of shifts with them just like we did before.
Are we going to have just like questions like that though, where it's like we have to plug in an x and there's a -2 next to it?
Right. So like,
Because like would that affect the exponent?
right. So that's what it would be doing. So technically, go back and kind of look at our points that we plotted. So for example, when x was 3, plug it in. What's 3 minus 2? 1. What's 2 to the first power? 2. So we were able to graph it without actually having to pick our x's and plug them in and find our y's. Does that make sense? But our shift is accounting for exactly what you said. Like any x we would pick, we technically would subtract 2 from it and then raise 2 to that power. But by knowing our shifts, we didn't have to do any of that. Okay? So that's exactly what we're going to do in example 4. What is technically the base in this function?
What, the 0.5?
Okay, so that's good to know. So we got to kind of like dissect 0.5. What's happening here? So he's the base. What's this negative on the outside do?
Wouldn't that like flip it?
About which axis?
The x?
Yep, so this flips about x. And then what's this positive 5 on the outside do?
Doesn't it like stretch it?
Nope. So that would be if this was multiplied by 5, but this is just a 5 added to our function. You're just used to seeing him back here.
Oh, we're just making him go up.
You got it. So this shifts up 5. So what we're going to do is we have 2 shifts. So we're going to graph our parent function here. What does he look like? We're going to reflect him first because it's always when you have multiple things going on, it's always take care of what's closest to your function first. So this negative's closest first, so we're going to flip it first, and at the very end, we're going to shift it up 5. Okay? So let's graph our parent. So this is our parent. And let's write it as 1/2 like that. So we can just kind of think, okay, when we flip it, what does it become, right? So the points I always pick are -1, 0, and 1 for my exponents. So when you raise 1/2 to the -1 power, you're just flipping it. So at -1, what is our y value going to be? 2. So let's plot -1, 2. And then what is always your y value when your x is 0? 1. And then what is 1/2 to the first power? It's just 1/2. So notice it's going to be that exponential function that's going down because we have a base between 0 and 1. Again, if you wanted to, you could raise it to the -2nd power, which means you would just flip it and square it. So if you flip it, it's 2, square it, it's 4. So you can graph -2, 4 if you need an extra point. I'm not going to make you do the extra point, though. As long as you graph those 3, it will be enough to see what's going on. So notice again, our horizontal asymptote still so far just kind of sitting at our y-axis. All right, what's the next move we're going to do? We're going to reflect it about the x-axis. So what's that mean? It means our x values are going to stay exactly the same, but we're just going to flip our y's, right? So we were at -2, 4. Now we're going to be at -2, -4. 1, 2, 3, 4. We were at -1, 2. Now we're just going to be at -1, -2. 0, 1 becomes 0, -1. 1, 1/2 becomes 1, -1/2. And again, you kind of see the curvature, but now it's kind of going to the infinity direction. And then this still rides that x-axis as a horizontal asymptote. Is that okay so far? It's kind of hard to graph it upside down, I feel like. All right, so then our last move is to add 5 to all of our values. So we're going to up 5 units, or however you want to make a note of what we're doing, okay? So what we're going to do again is kind of play a part, like pay attention to where your y values are. So at -2, we were at -4, so if we go up 5, we're going to be where? 1, perfect. At -1, we were at -2, so if we go up 5, we're going to be at 3. At 0, we were at -1, so if we go up 5 units, it's going to be at 4. At 1, we were at -0.5. So if we go up 5 units, we'll just be at 4.5. And what kind of helps you stay in line is that not only is the whole graph shifting up 5 units, but so is your horizontal axis, right? So if your horizontal axis was at 0, it's now been shifted up to 5, y equals 5. So you can even go graph that if you need to. So 1, 2, 3, 4, 5. So you know for a fact it's not going to go past this. Okay? So I'm going to make a note of that. Our horizontal asymptote has now become y equals 5. But recognizing that, it makes it easier to graph, so we know that, okay, after 1, 4.5, we're not going up a whole lot in our y values, right? Because we can't go past that 5. Any questions?
Are we gonna have to do it with just one graph on the test?
I'm trying to think,
Because this seems
I know,
like-
I'm trying to think, I need to play around with it, because what I liked about the last test was you never had to kind of memorize the parent function, you just need to know what the shifts did. So like one way I could ask this was, just tell me what I'm doing, and you could say I'm reflecting about the x-axis and going up 5. But what's special about exponential is that they are a special kind of graph. They're not your typical polynomial or whatever. So would you prefer to have multiple graphs to show all your steps, or are you okay just doing it with one?
I'd like to have multiple graphs.
That's how I am too. So because
It seems different than the other.
well, and I just think too, doing the reflecting and then trying to shift it up is kind of hard because it's not staying at 0, right? Like with a parabola or even the cubic feature, you were always at 0. So when you reflected, guess where you still were? At 0. But this one, when you reflect, you go from 1 down to -1. So shifting it up 5 only puts you at 4. Like it's hard to keep track of it all. So I think I would do like give you as many graphs as many transformations you had. So since this had 2 transformations, I gave you 1 for the original and then 2 extras. The one that we did on the bottom of page 2, it only had 1 transformation, so I gave you 1 for the original, 1 for the transformation. And I can do that. And I probably wouldn't do more than 1. So it'd either be like a shift left and right, or a reflection and then right, or something like that. You probably wouldn't have more than 2 things going on. Because it'd start taking up a whole lot of room at that point, because you'd have a lot of graphs there. Okay, so why exponentials are so different, and so because there's a lot of things in real life that follow it. So I know you stepped out of the room, but on page 2, I was just showing you an example of a real life situation where something grows exponentially. In this case, it's cell phone usage. So it doesn't follow a line at all, and you can grab this from me later. You don't have to worry about hurrying and writing it down. It doesn't follow a line, because we were just talking, Braden and I were just talking about, a line is just consistent. As years go by, cell phone use is going up the same amount every year. And that's not the case. You can see somewhere around here, like the late 1990s, early 2000s, it starts to go up pretty quick. And it was pretty plateaued in the beginning. So at the bottom of page 3, guess what else has an exponential growth? Investing, money, okay? So it says the amount of money of a principal P. So principal P is the starting amount that you either borrow or invest. So it can either be the loan you take out or the money that you put into an investment. After T amount of years, and an interest rate of R in decimal form, is compounded in amount of times each year. So compound interest. So simple interest, like what we have in our savings accounts, it's not exponential. But if anybody talked to you about CDs, like invest in a CD. I don't even know what CD stands for, but is that old school?
No, I mean, that's still a term.
And then IRAs, that kind of stuff, it's going to be something where it's a little bit more complicated than just simple interest. And so it potentially could have, if you're compounding it more than once a year, it's called compound interest. So let's just make a note of it right here. Compounded in times means how many times each year? How often each year? So off to the side, we're going to write some terms, and you guys are smart enough that you probably figure it out, but if not, I want to make sure you're using the right number. So if it's compounded annually, how many times a year is that? Once. So n would be 1, correct? If it's compounded semi-annually, twice, so n would be 2. If it's compounded quarterly, you got it. Is this making sense, Gavin? Monthly, 12. Weekly,
12 times 4, what's that?
no, because there's more than 4 weeks in a month. There's 52 weeks in a year. Right, we're off by a little bit, right? We have about 31 days each month. And then daily, 365, you got it. So that just kind of keeps you, and there's other ones too, trimesterly, like every third month or whatever. Okay, so that's the different things we can use for N. T is always how many years are you doing it. So like say you invested it for 10 years, but you did it quarterly, it got compounded 40 times, right? So P is always your starting amount. So your principal is always your starting amount.
You only got 5.
Okay.
4 minutes left.
Yikes. Okay. And then T is the number of years. And then R is your interest rate in decimal form, meaning divide by 100. So I think I'm going to stop right there and then pick up because I don't want to.